Hi, so today we've got another piece of expensive medical equipment to take a look at. This is an Aura XP laser. This is a 532 nanometer green 15 watt laser used for ear, nose and throat procedures. This uses a fibre optic delivery handpiece, which I don't have, and there are some contacts around that connector, so I'm sure it does some communications with it, so I don't think we'll be able to get it working in its sort of normal mode. Although I think it does actually fire the laser during some initial test and power up calibration and stuff, so might be able to get something out of it. This is a Flashlamp pulsed laser with an active Q switch on this. Although it's advertised as a continuous wave laser, it's obviously a pulse. It's working in a pulse mode, but probably up to fairly high frequency to act as if it was a continuous wave laser. On the front we've got a few controls here. Aim beam, so that's probably typically like a red laser diode to provide beam aiming. Got an emergency stop. This was a key switch, which I didn't have the key for, so I just replaced it with a latching push button. First connections on the back, there's a couple of vents and a fill port. This is filling the internal liquid cooling system. There's like a radiator and an internal closed loop cooling system in here. There's a connector for the foot pedal, a sort of pipe connector, because this is a pneumatic foot pedal, so there's no electrical connection, it's purely pneumatic. There's another connector marked for eye protection filter. I'm not quite sure why that's an electrical connection, unless it's one of these sort of like these automatic welding mask type things that darkens on demand. Remote interlock. And that'll be used, for example, perhaps connected to a door switch on a room where the surgery was being performed, to shut the laser off if someone comes in. There's a service port. I think this has some sort of dongle that plugs in to enable service functions, which unfortunately I don't have. It's got the IAC 16 amp mains in that. The power rating on this at 230 volts is 15 amps. So opening it up, we've got on one side what seems a slightly ridiculous amount of electronics, and on the other side some more power stuff. I would imagine this is probably to do with the controlling the flashlight. There looks like some high voltage stuff there, and some fairly serious shielding, strapping to probably to avoid issues from the high voltage ignition pulse of the flash tube, because that'll have a very fast rise time, so that's plenty of scope for causing various electrical havoc. And here we can see this is the cooling radiator, the reservoir tank, and there's a few bits behind there we can't quite see yet. I think this white thing is maybe a liquid filter, and on the top we've got this plastic cover that covers up all the laser goodness. And this is the switch for the pneumatically operated foot pedal. And here's a slight curiosity. We've got two fuse holders with the other end not connected to anything, and a spare connector here. Now these go into a big toroidal transformer, so I'm wondering if this is maybe to supply a non-fitted option or possibly voltage selection by sort of connecting one of these to here. I'll have to take a bit more of a delve into that and see if we can figure out what's going on there. Take a look at the laser stuff under this cover. Now it's quite interesting. It's a bit hard to immediately figure out what the beam path is, because they sort of folded it. And in here, this is the frequency doubling crystal, the KTP crystal, which looks like it's mounted on some Peltier coolers to control the temperature. The cooling fluid passes through here as well, and of course the coolant passes through here to cool the flash tube, which is going to be the main producer of heat. Some handwritten serial numbers there for the lamp and the YAG laser rod. And here's the aiming laser. This is probably going to be a red diode laser passing through this filter to fire a red beam down the beam path to help you point it at the right place. And this is all mounted on this very big, sort of chunky aluminium base. That's probably about 10mm thick, so that's obviously for mechanical stability. And down here there's a solenoid operated shutter. Down here there's a solenoid operated shutter that lifts this out of the way. But just also see there's a couple of photo interrupters behind there. You see a couple of photo interrupters behind here, which are to detect the shutter position, to make sure it is actually in the position the system thinks it's in. Interesting little note here about the about patents. It looks like this laser assembly is made by Laserscope, and it looks like they've licensed the use of the KTP crystal for medical use only. So I suppose technically you'll be breaching their patent if you use this for something other than medical. Now it took me a while to figure out the beam path on this, because it's actually not entirely straightforward. If we start from here, so this is basically the high reflective mirror. It goes through the KTP doubler, onto this mirror, down to this one here, through the cavity, back through the cavity, and then out reflecting on this mirror here down to the handpiece. So I think maybe if we get this, try and get this into its power up calibration mode, we'll actually see something happening. Yeah, the water pump going, and we're getting a warm up message on the screen. So it's turned the lamp on, probably to get everything warmed up. Not seeing any evidence of lasing, so the Q switch is probably closed. Now, from memory, last time I fired this up, it took quite a while the first time, but once the coolant was up to temperature, it actually fired up quite a lot quicker. Yeah, I just checked across these two fuses, about 10 volts between these two fuses, so I'm guessing that's probably for some extra peripheral or hardware or something. So I've got some green stuff happening, so it keeps doing it at various different levels. Now it's just telling us to attach a device, so it's obviously looking for the handpiece, which it hasn't got. So with a bit of smoke you can actually see the beam path. Interestingly, we didn't see anything at all going through the laser cavity, so obviously we've got the frequency doubled, 532 nanometers path going through sort of going through here, and it's only going to be the infrared 1064 sort of going through the actual cavity, which is interesting. Draws about 400 watts in this sort of standby mode. It pulls about 1400 watts when it's going at full power. Let's see if we block the that beam, the green disappears, so we just can't see it because it's infrared. Something I noticed when it's running is that this isn't actually a shutter, it's actually a mirror that just sort of fires the beam down into a sort of beam dump into this block of aluminium. Because obviously a fairly lightweight shutter is going to get hot if it just has to absorb all the beam. Now it looks a bit of a pain to try and defeat that shutter in a way that the sensors don't detect, because this is all one piece, so I don't think I'll bother. There is a lens at that front, so it'll probably just splay the beam out anyway. So a couple of little details here. There's this angled mirror, so that's going to be taking this beam and firing it down to some sort of sensing and measurement. There's also a secondary one there, which is the other side of the shutter, probably doing a similar sort of thing. And so there's also this other. Delve a little bit further. I don't think it's really worth preserving this as a working unit. So it's 15 watt green laser, you can pretty much buy those solid state ones for very little money. So I don't think there's actually a particular value in keeping this as a laser, because obviously it would be quite a pain to actually get working. So you'd have to get all the power stuff to control the tube, and so it'll be pulling about a kilowatt for producing 15 watts of light. So I think we're going to go full teardown on this. Apologies to any laser purists that find that offends, but a 15 watt laser that takes a kilowatt, I don't think it's a particularly useful thing. Okay, so it actually turned out not so hard to get that shutter off, so I've bypassed that and put a cover over the light sensor forward of it and put a chunk of wood in front of it. Let's just see what happens. One thing I didn't check is, I suppose if it was being ultra cautious, it would actually activate the shutter and check that the shutter switches were working. I don't think I noticed it doing that, so let's just see what happens. I've taken the lens out of the front as well, so in principle this should shoot the laser straight out the front of that piece of wood. Let's see what happens. Nice. So taking a closer look at this PCB, it's sort of pretty old school. So the processor in this is a 80C188, it's a fairly ancient embedded Intel jobby. Bit of RAM, Dallas non-volatile storage, Epson LCD controller here, ROM for the software. Interesting, there's a couple of Altera Max FPGAs on these sort of carrier boards. These are probably just like a package availability thing, so they couldn't get them in PLCC, so they put them on these little carrier boards. There's actually some sign of liquid corrosion on these pins, so I'm a bit surprised this is still working. These are all just I/O chips. And then there's a couple of areas where you can see there's an outline for a CAN. These are the optical sensing parts to actually measure the laser power. The back where those beam splitters went to feed some of the power forwards. And those are picked up by these photodiodes here on the back of the board. So this does look sort of quite significant overkill, but I think a lot of that's just due to its age. Obviously once you've got a medical device sort of approved, then it's quite a lot of work to then make any changes. This case is all welded together, so all this stuff clearly has to come out sideways. This cover over it, which has got this lip on it, so I'd imagine that's probably just to catch any coolant leaks and divert them away from the high voltage electronics. Okay, so this is the power supply board on the other side. Nothing super interesting here. There's a backlight inverter for the display, various voltage regulators. There's a bit of main switching. I think there's a relay that switches mains to various other parts, possibly the circulation pump. Haven't found that. I'm not sure if that's a mains or a low voltage thing. So there is a big toroidal transformer in here somewhere. I'm not sure exactly what that powers. Current sensing to measure the power draw. There's a couple of power resistors. I think these are probably the ballast for the lamp, because there's like a shielded wire going to that with quite a lot of ferrite, so that would be to suppress the spike from the ignition pulse on the lamp. There's sort of one ferrite there, another one there, and another one there, so they're clearly quite concerned about that. And there's some you can see where the shield's grounded there, and also there's another one there. So obviously they put those resistors there for heat sinking, but they wanted to make sure that the ignition signal didn't cause havoc with the rest of the electronics. So this looks like the lamp power supply. It's actually a company Analog Modules Inc., so maybe that's manufactured by somebody else. Takes mains in. It says 300 volts DC maximum output. Interesting little tree of power resistors. The UC3841 power supply controller. Turn this over. On the other side we've got a big ass heatsink, a couple of power devices, thermal cutout switch on there, a couple of massive inductors. So I'm guessing this is probably a sort of boost regulator type setup. Massive great diode here, great big 20 microfarad 250 volt non-electrolytic cap down there. It's a bridge rectifier. 2200 off 200 volt caps, 4 of those altogether. So yeah, just a big, probably a DC current regulated, maybe programmable current power supply, because I'd imagine that's how they adjust the laser power, is by controlling the lamp current. I think this is the board that controls the ignition of the lamp. So these discharge lamps will have like a DC supply and then need a very high voltage supply just to strike it to start the plasma discharge. So it's probably going to be working by discharging this cap through this thyristor into a transformer, which we can just about see the high voltage symbol on the back here, and that'll be connected in series with the DC supply to the lamp. So it injects a high voltage spike on the supply to do the initial ionisation. Okay, next in, this is just a voltage regulator for the Q switch. The actual main supplies here, these are driven by a RF signal to modulate their optical properties. So the idea of a Q switch is that it can be transparent or let through the light, so it allows energy to build up in the lasing medium, in this case the rod, and it will suddenly turn on to produce very high peak powers. Very common technique in lasers. And inside here we can see there's a big chunk. There's a 60 watt power MOSFET designed to work up to about 900 megahertz. There's an Altera UPLD in there, DC-DC converter, and a few various analog bits and pieces. There's not much in the way of interface to the rest of the system. There's just these 3 wires, which I'm guessing are probably just power, maybe power and 1 data, and then there's a coax, which will probably be just the on-off control. And this will be the ignition transformer to provide the high voltage pulse to strike the lamp. And here we've got the input mains filter. Obviously this is big because it's got 16 amp current rating to support the lamp current, so that's the main reason why this is so huge. Okay, now I've got some of the rest of this stuff. We can see a bit more of the cooling system. Now, you may have thought that thin tubing we saw on the top was a bit lightweight for a 1 kilowatt heat source. Well, that's right, because here's the main cooling that's coming through the bottom. Massive great fan, and there's a circulation pump here. And we've got a little pressure sensor here. Here's the main power transformer. You don't often see these days. Custom made for laser scope in USA. Okay, so here's the cooling unit. Massive great fan, 12 volt pump which says 12 volt BLDC, brushless DC motor powered pump. That's just the reservoir tank on the right. And massive great heat exchanger made by Thermotron Engineering Inc. And I've got the optical deck off here. You can see some of these cooling tubes going to the Q switch and the heater on the KTP crystal. And there's also a pathway through the main lamp block. But the main cooling comes through here from these bottom tubes. There's 2 thick wires of the main connections to the tube. And this is the lamp block. You see the water inlets in the bottom, sealed with O-rings in the base plate. It sort of goes across and then back. I think these small tubes are just for venting, because obviously they're not big enough to carry any serious amount of water and they go into the same chamber, so I think they just avoid any airlocks or bubbles in the main section. So there's this plastic block on the end that goes into the an O-ring in the body. So this is the actual main discharge tube. I don't know, high pressure xenon or something may well be tuned to produce the maximum amount of the wavelength that the laser rod wants to absorb. And the laser rod's just held in by these 2 end plates with a couple of O-rings. Once those removed, we can just take it off. So this is the actual laser rod. It's got a fairly characteristic sort of slight pink tinge to it of the YAG doping, very highly polished ends of course. Now I was fully expecting this to be like a very highly polished assembly to like focus the image of the flash discharge onto the tube, but it's actually very diffuse. I wonder if maybe that's just to avoid any getting hot spots in any particular area on the rod. There's also this glass separator. Doesn't appear to have any optical coatings. I don't know whether that's maybe just to reduce the amount of UVC or possibly even to sort of protect the rod from a sort of exploding tube or something. But I've never seen something like that on a laser thing. It's just like a very diffuse reflector. It's like a sort of fairly soft sort of silicone type material, but obviously very bright white. And here's the Q switch module, which you can see is actually sort of clear in its unpowered state. You can see we've got this optical glass or crystal or whatever it is, and there's just the RF input, some sort of matching network, just some sort of coupling to that. My understanding is this basically sets up sort of standing waves, it's like a sort of piezoelectric type effect to modulate the optical properties of the material. And this is the handpiece interface. There's a micro switch to detect when something's plugged in. There's this light guide that goes back into one of the optical sensors. I wonder if maybe that's for detecting damaged fibre, because obviously if you've got a fibre that's cracked, that'll probably leak light out the side. So I wonder if maybe that's for detecting that situation. But so it's interesting that this isn't actually pointing straight at a beam splitter or anything. It's just sort of going sideways into this chamber. There's a sort of beam splitter here to measure the outgoing power, but this just seems to be sort of vaguely poking into that area, so I'm not quite sure what's going on with that. That's the connection for the handpiece. Seems to be a surprising number of connections on there, and I'd imagine there'd be sort of various ID and all that sort of things. Maybe there's some controls and measurements going on in there, but a surprising number of wires going to that. A close look at the KTP holder. So you can actually see the sort of crystal in there sandwiched between these 2 white blocks. And then there's a couple of what look like thin film heaters. There's obviously a thermal sensor there, and so those heaters are sort of heating this up, and then the water cooling is sort of just keeping that regulated, so it could just work the heater against the cooling to maintain a constant temperature. And obviously there's some adjustment to actually adjust the angle, because the alignment of this is going to be fairly critical. As you can see, there's a couple of points there with adjustment screws. So another bit of medical kit, which is pretty much probably all but obsolete by now. You can buy a 15 watt green laser on AliExpress for about £1 for Obviously that's a stage one rather than a medical one, but even so the tech now is just going to be a bunch of pump diodes, possibly maybe even a similar YAG rod, but somewhat simpler and cheaper.